Welcome to the journey of exploration with science and sleep. Let your eyes close, release the worries of the day, and listen as your own breath slows down. Tonight, we will step into a world that once existed hundreds of millions of years ago, a time when giant insects ruled the skies, and even the air itself was strong enough to shape life. In the dense ancient forests, strange plants reached high, while above, enormous wings flapped gently, casting mysterious shadows onto the ground. This is not only a story about creatures, but also a mirror reflecting the deep connection between Earth, evolution, and ourselves. So if you are curious to know what created that magnificent era, stay tuned until the end of the video, and don't forget to hit subscribe and the notification bell so you won't miss the next scientific journeys. Imagine you are stepping into an ancient forest where light filters through enormous canopies, unlike any forest on Earth today. Um, there, the trees are not the familiar oaks or maples, but living pillars rising from swampy ground, towering high, covered with rough scales, like carved stone towers. Some of them reached higher than old cathedrals, up to 30 meters above the ground. In the open spaces beneath the canopy, ferns spread their fronds like gigantic fans, and horsetail trees grew in clusters, their segmented joints stacked like bamboo stalks, forming a dark green, damp, and tangled wall. The ground beneath your feet is not solid soil, but a soft, spongy carpet of decayed vegetation, giving the sensation of walking on a sponge. From time to time, dark pools of water appear, flat and still like mirrors, waiting for a gust of wind or the shadow of an insect gliding past to stir their surface. The air is thick, heavy with moisture, and saturated with the scent of rotting plants. It clings to your skin, making each breath feel denser, richer in oxygen than the atmosphere today. This was the invisible substance that shaped the giant creatures of that age. For in the Carboniferous period, more than 300 million years ago, Earth was like an open laboratory, where the very air itself changed the scale of life. Atmospheric oxygen levels surged, at times reaching nearly one-third of the total volume of air. To put this in perspective, remember that today we breathe only about 21% oxygen. That difference created a strange world where flames ignited more easily, dry leaves could catch fire faster, and even damp wood risked turning into glowing embers from a single lightning strike. At the same time, this oxygen rich environment became a hidden reservoir of energy, igniting a new chapter for animals dependent on gas diffusion. Unlike mammals or birds, insects have no lungs. They breathe through tiny spiracles along their bodies, leading into a network of tracheal tubes branching into the tissues. At small sizes, this system works perfectly. Oxygen diffuses quickly, directly into each cell. But as the body grows larger, diffusion distance becomes an obstacle. In today's atmosphere, that has imposed a strict limit on insect size. However, in a time of abundant oxygen, that barrier was broken. Diffusion became stronger, faster, enabling insects to expand into scales once thought impossible. That is why in this forest, if you look up, you might see wings nearly a meter across sweeping through the sky. These were griffin flies, giant ancestors of modern dragonflies. They did not merely fly, they dominated the skies like dark shadows gliding through the twilight. Below, ancient millipedes stretched over a meter long, their segmented bodies moving gracefully like short trains, weaving among roots and decaying leaves. The sight was at once familiar, still insects, yet utterly alien, magnified to overwhelming proportions. But the story is not just about gigantism. More importantly, it reveals a delicate relationship between the atmosphere and evolution. Plants of the Carboniferous thrived, many of them without seeds as we know today, reproducing by spores, growing densely in swampy wetlands. When they fell, their remains often did not fully decompose. Instead of being broken down by microbes and returning carbon dioxide to the atmosphere, they were buried, compressed into coal. Each layer of trapped vegetation meant oxygen was not consumed but continued to accumulate in the air. The result was a strange feedback loop. Forests grew, forests fell, carbon was locked away, oxygen rose, and creatures that breathed through diffusion flourished. The atmosphere, in this way, was not merely the backdrop of life, but an active character, a force shaping the boundaries and possibilities of species. If you listen closely in that forest, you will hear more than the wind and the water. You will hear the heavy wing beats of flying insects, their sound echoing more slowly in the dense air. You will hear the plopping descent of an amphibian slipping into the mud, the rustle of massive leaves swaying like a vaulted roof. And when night falls, the whole forest glows with greenish bioluminescence from fungi on decaying wood, a chance byproduct of chemical reactions and decomposition. This scene offers a lesson. Life and atmosphere are bound so tightly that a change in one inevitably transforms the other. Giant insects were not random monsters, but vivid evidence of the fragile balance between chemistry, biology, and climate. They grew because the world allowed it, and when the world changed, they faded away. Thus, the age of giant insects is like a mirror, showing that Earth is never still. The air you breathe today is the outcome of millions of years of trees, swamps, fires, and the vast wings that once stirred the skies. And if we are patient enough to look closely, every story of the past reveals a clue about the deep connection between this planet and the life it harbors. Looking back at the Carboniferous period, more than 300 million years ago, we enter a world both alien and strangely familiar. Vast giant forests stretched out, where towering tree ferns and lycopsids covered the skies, creating a density of vegetation never seen before. Each fallen trunk in the damp swamps was buried instead of fully decomposing, gradually forming layers of coal, a legacy still exploited by humans today. But there was an unexpected consequence. The more carbon was locked away underground, the higher the oxygen in the atmosphere rose. And that very abundance opened up a golden age for six-legged creatures. Insects have always been masters of adaptation. Their tracheal respiratory system, entirely dependent on diffusion, usually limits body size. In today's atmosphere, a cricket or dragonfly may grow to a few centimeters, with only rare exceptions reaching large proportions. Yet in the Carboniferous, when oxygen levels soared to nearly 35%, that limit suddenly shifted. The tracheal tubes could deliver oxygen throughout the body without clogging. Thanks to this, ancient dragonflies such as Meganura could possess wingspans of over 70 centimeters, comparable to a modern bird of prey. Imagine, in the gloomy skies above ancient swamps, those giant insect airplanes gliding lightly through shafts of light filtering down, their wings shimmering like stained glass. Not only dragonflies, but many other species reached sizes that astonish us. Millipedes related to Arthropleura once crawled over 2 meters long, moving across carpets of decaying leaves with a form both majestic and intimidating. They were not fierce predators, but mainly fed on rotting vegetation. Yet their sheer size made them symbols of an era when surplus oxygen expanded all biological boundaries. Even scorpions, spiders, and many ground-dwelling insects were far larger than the familiar images we know today. That world must have been both spectacular and perilous. In an oxygen-rich atmosphere, fire ignited more easily. Fossil charcoal found in ancient sediment layers shows frequently swept through and consuming vast stands of giant trees. But this very cycle continued to maintain high oxygen levels because partially burned plants were buried, carbon remained trapped, and oxygen continued to accumulate. It was a dual feedback loop of forest, fire, and air, proof that the biosphere and atmosphere were always bound together in the dance of evolution. With the advantage of abundant oxygen, insects were not only larger but also more active. Enormous wings could beat longer, powerful legs supported stronger exoskeletons, allowing them to conquer every corner of the ecosystem. A giant dragonfly could hunt prey that no insect today would dare to attack. The dense, swampy wetlands became battlefields of these large winged warriors, where flight speed, muscle power, and direct respiration became ultimate weapons. But within this prosperity lay the seeds of its own limits. As the Carboniferous period ended, Earth's climate began to change. The shifting of continents, changes in the carbon cycle, and the emergence of gymnosperms, with more efficient reproductive strategies, transformed the environment profoundly. Vast swamp forests gradually disappeared, atmospheric oxygen declined to levels closer to what we know today. And as that blanket of oxygen was drawn away, the giants that once ruled sky and land quietly vanished. This is one of the clearest proofs that evolution is not always a story of upward progress, but of constant adjustment to the planet's physical and chemical conditions. Giant dragonflies or millipedes did not disappear because they were weak, but because the atmosphere no longer favored them. When oxygen returned to normal levels, physical limits closed in once more. forcing insects to shrink in size to survive. This contraction also opened up opportunities for other animal groups, especially reptiles, to rise and take over ecological niches once hidden under the shadows of massive wings. What is fascinating is that today we still see echoes of that era in the forms of living species. Modern dragonflies, though only the size of a hand, still retain masterful flight skills, able to beat their wings independently, hover motionless in midair, or dart with astonishing speed. Millipedes and centipedes today, though only a few centimeters long, still carry the shape of their giant ancestors. The tiny spiracles along their bodies, the intricate networks of tracheae, are still the legacy of a biological design once strong enough to sustain creatures many times their size. Seen in full, the Carboniferous period offers us a double lesson. On the one hand, it shows the power of the atmosphere. Just by altering the proportion of oxygen, the entire world of living creatures could change in unimaginable ways. On the other hand, it reminds us that every biological system is bound tightly to physical laws: diffusion, the ratio of surface area to volume, the trade offs between water and air. Giant insects once existed not because of miracles, but because of a rare harmony between biological design and favorable atmospheric conditions. And that is why studying the giants of the Carboniferous is not just a scientific fairy tale. It is also a reminder that our planet is always changing, and life is always responding in unexpected ways. Who knows if in some far future Earth's atmosphere transforms once again, might giant insect wings return to the skies? In that setting, we can picture a world where every breath was an invitation to abundance. The air was not merely an invisible backdrop for life to unfold, but an active force driving new forms of body and behavior. With the pressure of abundant oxygen, insects did not simply grow larger, they redefined how to interact with their surroundings. A half-meter wingspan was not only an advantage of speed, but also an opening into hunting spaces never before available. A giant millipede, as long as a human, was not just an inflated version of its old form, but a complete transformation in how that creature dominated the ground, forcing every other species to adapt to its heavy, constant presence. What is fascinating is that this evolution did not happen in a sudden, random burst, but was the result of long rhythms between climate, chemistry, and biology. As oxygen rose, the physical limits of the tracheal respiratory system suddenly widened. No longer did oxygen molecules have to squeeze through tiny tubes, but instead flowed abundantly, like a flood season river brimming with fresh water. Bodies once bound by the laws of diffusion now felt unshackled, experimenting with new dimensions and roles. Yet the power of the atmosphere did not stand alone. Remember that the Carboniferous forests were not merely the backdrop, but the living stage where trees and wetlands created an endless feast. This richness allowed giant bodies to exist without falling into scarcity. Trunks dozens of meters tall, leaves falling thick to form carpets, and swamps constantly depositing nutrients, all together built the vast biological banquet table. Insects, ever the most efficient recyclers of organic fragments, were suddenly pushed into key roles in material cycling. They were not just scavengers, but diligent workers of the ecological machine, cutting, grinding, and initiating the decomposition processes that microbes were not yet powerful enough to finish. A vivid picture emerges when we look closely. In the darkness of the swamps, tiny ancestors of beetles gnawed on the soft parts of dead leaves, creating countless fragments. On the damp ground, giant millipedes marched like trains, turning vegetation into crumbled humus. In the skies, griffin flies with compound eyes swept across the air, hunting weaker insects, maintaining balance in the food chain. Even in murky waters, predatory insect larvae lurked, sharp jaws ready to seize any prey that swam past. Every ecological layer, from treetop to streambed, echoed the mark of the atmosphere: rich in oxygen, rich in potential, and rich in contradictions. But every prosperity has its limits. As forests continued to draw down carbon dioxide, storing it in undecayed trunks, oxygen rose even higher, fueling wildfires of unusual intensity. Forest fires were not only disasters, but forces shaping the landscape, producing thick layers of ash alongside peat. The Carboniferous forests wrote their own cycle: growth, collapse, blazing fire, and regrowth. Within that whirl, insects were not only beneficiaries, but witnesses of immense cycles of creation and destruction. If we compare this period to a symphony, oxygen was the invisible conductor. When the baton was raised, the giant orchestra played, insects beat their wings, forests stretched skyward, wetlands resounded. When the baton fell, the rhythm shifted, wildfires, floods, and finally the decline of oxygen as the Carboniferous came to a close. It is hard to find clearer evidence for life's dependence on the atmosphere, not as a silent foundation, but as an active agent, a companion and co-creator. Today, when we look at the fossils of dragonflies with half-meter wingspans or the bite marks on ancient leaves, we are not merely seeing the shapes of extinct species. We are seeing the ink marks of an ecological contract between life and the air, a contract with an expiration date. When oxygen retreated to a new balance in the Permian, those giant bodies lost their place. They disappeared not because evolution had gone wrong, but because their pact with the atmosphere had expired. That gives us a profound lesson. The limits of life are not written only in DNA, but inscribed in the air we breathe, in the climate that surrounds us, in the cycles of carbon and oxygen. The giants of the Carboniferous could exist only because Earth then permitted it, through atmospheric chemistry and the slowness of microbial decay. When conditions changed, nature did not hesitate to erase those giants. And perhaps it is the brevity of that era that makes it so memorable. It shows us that life on Earth is not a straight line of endless growth, but a series of great experiments. Some experiments last hundreds of millions of years, some only a geological blink. Giant insects were one such experiment, spectacular, brief, and deeply evocative. They remind us that even the invisible gases around us are silent authors of evolution's story. And who knows? If one day Earth's atmosphere changes again, nature may well write a new chapter with forms of life far beyond what we can imagine today. Arthropleura, the giant millipede of the Carboniferous period, was not a creature you could easily overlook. At more than 2.5 meters in length, wide enough to block a narrow path, it was a vivid symbol of what Earth once nurtured in its oxygen-rich atmosphere. Its body was built from dozens of armored segments, each bearing a sturdy pair of legs, creating a rhythmic movement like a biological machine. Imagine each leg lifting, lowering, pressing against the layer of decayed leaves, the sound echoing like steady drum beats in the damp darkness. If flying insects like Meganeura ruled the skies, then in the damp ground below, Arthropleura was the silent lord, diligent yet impossible to ignore. Fossil traces found on today's North English coast show that these creatures did not exist alone. They may have moved along swampy shores, leaving deep grooves impressed into the soft ground. Scientists debate whether they actively hunted or merely scavenged decaying plants, but most agree that with such size, their diet must have been diverse. A small insect, a juvenile amphibian, even a decaying tree trunk could have been a feast. The ancient world allowed no pickiness, and the reward for flexibility was survival for millions of years. Try to picture yourself standing before Arthropleura, its shiny brown exoskeleton divided into plates like a suit of armor, both flexible and strong. Long antennae wriggled ahead, probing the environment, sensing the faintest vibrations in the soil and air. As it moved, its entire body resembled a rolling wave, slow but powerful, a reminder that you were facing a creature far beyond the norms we know of modern insects and arthropods. Its gigantism came not only from its genes, but from the very conditions Earth had designed: high oxygen levels, a humid climate, and an ecosystem without effective competitors. The fascinating thing is that in our eyes, Arthropleura may look terrifying, a giant centipede crawling through a coal forest. But from its perspective, the world was entirely different. The ground was a vast domain, full of the smell of damp moss, rotting wood, and glowing fungi. With no birds of prey above and no predators on land, they wandered freely, slow but steady, like natural trains, unhurried by time. In a world where most creatures measured only a few centimeters, dragging a body several meters long was already a bold proclamation. This was the age of giants. The relationship between Arthropleura and its surrounding ecosystem was no less intriguing. When dense vegetation toppled after storms, rotting logs created a rich environment for countless small creatures. Insects, fungi, and young amphibians all crowded in to exploit this source of energy. And Arthropleura itself, with its enormous size, may have played the role of the cleaner of the coal forest. They broke down matter, churned the humus, helping cycle nutrients. If today earthworms are praised as ecosystem engineers, then in the Carboniferous, Arthropleura was perhaps the giant version of that role. But every glory has its limits. As Earth's climate changed and oxygen levels fell, a giant body became a burden. The tracheal breathing system, effective only in oxygen rich air, could no longer sustain a body several meters long. At the same time, the rise of new predators, reptiles, and later birds, stole away the safe space of these slow giants. Arthropleura faded not because it was weak, but because the world around it had changed, and in its disappearance, it left behind an important lesson. Gigantism exists only when the environment allows it. The fossils of Arthropleura are not just engravings on stone, but doorways into imagination. Each curve of its armor, each groove left in ancient mud is a fragment of a larger picture. That Earth once nurtured life forms far beyond our everyday understanding. Giant armored trains, insects with wings wider than a crow, swamps glowing with fungi, all truly existed, not just in myth. Today, when we see a small centipede crawling in the garden, few would think it is a distant descendant of the giants that once ruled the land. But the memory of Arthropleura remains, etched in stone, resonating in imagination. It reminds us that what is small today may once have been the masters of yesterday, and that strength lies not only in size, but in the ability to adapt to the planet's ever-shifting currents. So when we close our eyes and imagine walking through the dark coal forest, listen closely. The crunching of decayed leaves, the distant wing beats of Meganura, and then the heavy rumble, a giant Arthropleura slowly crossing the path ahead. It is not merely the sound of a creature, but the heartbeat of an entire vanished era, a whisper from Earth that life can always surpass the limits we once believed. When we think of a creature like Arthropleura, we do not only see a giant insect crawling in the darkness of the Carboniferous forest. We are looking at a living testament to the resilience and opportunism of life. Each leg, small compared to its body, yet moving in perfect coordination, those dozens of pairs of legs did more than simply support. It represented an optimized system where the immense weight was distributed rhythmically with every step. It is hard not to imagine the faint sound of its armor scraping, the rustling of decayed leaves beneath hundreds of feet. Those steps, steady and patient, were the heartbeat of an era when nature was testing the limits of itself. In the setting of the Carboniferous forests, Arthropleura was not a lonely monster, but an essential link in the machinery of ecological recycling. Giant trees fell, dense leaves dropped, and thick layers of detritus accumulated. Without giant detritivores like it, the rate of decomposition may not have kept pace with the rate of deposition, and the forest might have become an endless green graveyard. Here, Arthropleura performed the work of a diligent recycler, shredding material, returning energy to the cycle. Its immense appearance may make us think of a mysterious giant, but in reality, it was more like a silent gardener, preserving the pulse of the forest with every bite of decayed leaves. There is something fascinating. The existence of Arthropleura was only possible thanks to the unique atmosphere of the Carboniferous period. Oxygen levels in the air back then were above 30%, compared to only 21% today. This not only allowed arthropods to breathe more efficiently, but also opened the door for body sizes to exceed usual limits. In that oxygen-rich environment, every breath Arthropleura took allowed its branching tracheal system to supply enough oxygen to nourish a body more than 2 meters long. One could say that the atmosphere itself nurtured this giant, a creature that today could never exist. And within this factor, we see a lesson about the fragility of adaptation. Arthropleura grew powerful not only because of its body structure or its feeding habits, but because environmental conditions aligned perfectly. When oxygen levels dropped in later eras, the strength that once carried it to its peak became a burden. A respiratory system that could not expand, an exoskeleton that grew ever heavier, and the emergence of swift vertebrate predators all combined to drive this lineage into a dead end. That makes us inevitably think of the concept of biological limits. On a microscopic scale, an ant can lift dozens of times its own body weight, but if you scaled it up to the size of a bus, its exoskeleton and muscles would collapse under its own mass. Arthropleura was a rare exception, proof that sometimes nature can temporarily bend the laws that seem unbreakable. But Such bending does not last forever. Imagine another scene. In the misty dawn of the Carboniferous, a giant Arthropleura has just completed a molting cycle. Its old shell, hollow, lies on the forest floor like an abandoned suit of armor. Beside it, its new body gleams, soft and glistening, as if freshly cast from resin. For hours, even days, it must hide in the shadows of massive tree trunks, avoiding exposure while still vulnerable. Here, gigantism is no longer power, but helplessness, a long, heavy body waiting on time itself to harden its new armor. That moment shows the raw truth. Giant does not mean invincible. It is only another fragile balance between life and death. But once the new armor hardened, Arthropleura returned to its majestic form. With long antennae probing ahead, it advanced across terrain filled with roots. When faced with a giant fallen tree, its segmented body flowed over it like a wave, each section rising and falling in turn, dozens of legs working together in a slow motion dance. Not agility, but certainty. Not slaughter, but patience. That very rhythm made it part of the forest's heartbeat, enduring, silent, yet indispensable. Today, when we look back at the traces of Arthropleura on sandstone, we're looking at a kind of fossilized memory. It is not only the imprint of its feet in soft mud, but the mark of an era when ecology operated in another way. Those tracks tell us that there was a time when life experimented with gigantic forms, and that it was not a show of excess, but a genuine solution to ecological challenges. To sustain balance, there had to be giant detritivores, just as there had to be towering trees. The disappearance of Arthropleura also reminds us of the impermanence of every advantage. What is a strength at one time can become a burden at another. Every organism is the product of a specific environmental moment, and when that moment passes, they no longer fit. For Arthropleura, death did not come from a single enemy, but from the slow, relentless changes of the atmosphere and the ecosystem. When we stand in a modern forest, hearing the faint hum of insects, it is hard to imagine that once those sounds were amplified into the footsteps of a creature more than 2 meters long. But if we listen to the fossilized traces, we realize that nature once dreamed in giants. Arthropleura was one of those dreams, a dream made of chitin and leaf litter, long gone, but still echoing in stone, in imagination, and in the lesson of life's fragile limits. In the intricate tapestry of the Carboniferous period, the gigantism of insects was not merely a physiological phenomenon, but also a story interwoven between environment, evolution, and biological limits. When looking at the wings wider than a hawk's of the dragonfly Meganeura, or the log-like living body of the millipede Arthropleura, people often tend to attribute it to a single cause: high oxygen levels. Indeed, atmospheric oxygen concentrations exceeding 30% turned every breath into a bountiful source of energy, expanding the ability to transport gases through the insect's simple tracheal systems. A respiratory mechanism that in today's world limits size suddenly became an open doorway, allowing them to reach proportions their descendants could only dream of. But this story, if confined to oxygen alone, would miss the vast and complex universe unfolding within those lush swamps. One important piece of the puzzle was the absence of terrestrial vertebrate predators in the early stages. At the time when giant insects reached their peak, amphibians had only just begun to step out of the water, while primitive reptiles remained modest in scale. This gap created an evolutionary pause, a temporary safe zone for insects and other arthropods. Free from the survival pressures of agile predators, they could comfortably experiment with new body forms, dominating the skies, the ground, and even the forest litter. While other ecological niches awaited occupation, insects spread their wings wide, displaying their colossal forms as a temporary assertion of power in a still young world. However, this advantage did not last forever. As reptiles began to thrive, armed with sharp teeth and agile locomotion, the terrestrial world became far more dangerous. Clumsy giants could no longer fly or crawl in absolute safety. An insect a meter long became an easy target, since great size came with enormous energy demands and poor concealment. In this context, being large no longer equated to being strong, and sometimes even foreshadowed decline. As the evolutionary balance tilted toward more agile vertebrate predators, many lineages of giant insects fell into retreat, giving way to smaller, more flexible, and resilient forms. Moreover, internal competition within the arthropod community itself played a key role. The Carboniferous swamps were no quiet paradise, but an ecological battlefield where countless species of centipedes, scorpions, and primitive spiders jostled for space. In such a system, maintaining gigantic size meant monopolizing abundant resources continuously, a task far from easy amid rising competition. The ecological niches were initially wide open, but as more and more species crowded in, the experimental space narrowed. Large size, once an advantage, gradually became a burden as the environment changed and rivals emerged. Alongside ecological factors, climate and geology themselves dictated the fate of these giants. Fluctuating sea levels, massive wildfires fueled by high oxygen concentrations, and climate shifts constantly reshaped the landscape. The swampy forests, once sanctuaries for giant insects, were sometimes reduced or replaced by drier environments. For species dependent on humidity and dense vegetation, such transformations were akin to the withdrawal of an evolutionary stage itself. When the ecological foundation wavered, gigantic body forms could not endure. What is astonishing is that, despite their inevitable decline, the legacy of giant insects still resonates today. Their fossils, from wings imprinted on thin slabs of stone to rhythmic trails left by legs in mud, recount a vivid chapter of nature's bold experiments. In them, we see not only failures, but also the ceaseless creativity of evolution. Every giant of the Carboniferous was a testament to a time when the limits of life were pushed further than ever before, only to be pulled back by the strict laws of the environment. When we look at this gigantism, we learn something profound. No advantage is absolute. Every benefit is bound to its context, and when the context shifts, what once empowered a species can turn into a burden. High oxygen, the absence of predators, fertile swamp forests, all converge to open a strange moment in Earth's history where insects reached unimaginable sizes. But that moment was only a short chapter in the vast chronicle. As the environment shifted, predators appeared and competition intensified, that resplendent gigantism quietly closed. And in this blend of glory and fragility, we perceive more clearly both the power and the limits of evolution. The giant dragonfly wings imprinted on stone are not merely relics, but reminders that life is ever changing, ever experimenting, and nothing is eternal. They stand as proof that nature never ceases to create, even when some creations exist only fleetingly in the dim light of the Carboniferous. In the moment of gazing upon the fossils of the Carboniferous giants, we do not only see the past, but also the eternal laws of life. Glory and decline, prosperity and extinction, all revolve around the fragile balance between organism and environment. Wings as wide as a raven's shadow, bodies as long as moving logs, they were once symbols of an age when Earth allowed life to exceed the usual limits. Yet when the air, the climate, and the ecosystems changed, that very gigantism became a burden too heavy to carry. The wonder lies in this. Although they vanished, their legacy endures in every fossil story, in every vein of ancient leaves, in every piece of coal we touch today. The giant insects teach us that evolution never ceases to experiment, and that every standard is only temporary within the whirl of time. In understanding this, we come to cherish the present diversity even more and grow more curious about the other experiments nature once carried out, secrets that perhaps we have never yet witnessed. When looking back at the past, people often imagine the Carboniferous as a world both familiar and strange. Ancient forests grew densely, with tree trunks towering many times higher than any modern species. Sunlight rarely reached the ground. Instead, the atmosphere was dim, saturated with humidity and mist. In that setting, giant insects flew and crawled everywhere, creating a vision half dreamlike, half nightmarish. It was the unique combination of atmospheric conditions, ecosystem structure, and evolutionary pressures that paved the way for such creatures to exist, at least for a fleeting moment in Earth's history. One of the reasons the Carboniferous became a paradise for giant insects was the high oxygen concentration. At levels of 30 to 35%, the atmosphere at that time was almost an inexhaustible reservoir for tracheal respiration, the characteristic mechanism of insects. At that moment, oxygen was not only sufficient to sustain larger bodies, but also allowed them to maintain predatory activity and flight without being limited like modern insects. By comparison, breathing in an oxygen-rich atmosphere was like an athlete being supplied with endless energy. Insect bodies required no further improvement to scale up. But like any ecological advantage, this condition did not last forever. Within that realm, the most striking was the genus Meganura, also known as the griffin fly. With wingspans reaching up to 70 centimeters, they were among the most successful aerial predators of that era. Imagine walking through the forest and seeing a creature resembling a dragonfly, but with wings as wide as a laptop, gliding above your head. Although it may sound terrifying, in reality, they were still insects preying on smaller creatures rather than monstrous beasts of destruction. Calling them prehistoric monsters reflects human imagination more than scientific truth. That truth, that an insect could grow to such a size and still function efficiently, is astonishing enough without embellishment. Not only in the air, but the ground of the Carboniferous also displayed remarkable feats of size. Arthropleura, a distant relative of the millipede, could reach lengths of up to 2.5 meters. Rather than a grotesque predator, evidence suggests they were plant and detritus feeders. Imagine a giant walking log, slow, heavy, yet harmless. The existence of Arthropleura demonstrates that in a nutrient-rich ecosystem, even plant eaters could achieve enormous sizes. Yet biological constraints, such as their exoskeleton and the need to molt, shape the fragility of their evolutionary trajectory. At the same time, ancient rochoid species, distant ancestors of modern cockroaches, also left their mark. Instead of the tiny cockroaches we see today, some ancient species were nearly as long as a smartphone, not quite dog-sized monsters, but still large enough to make modern humans shiver. Interestingly, while giant insects gradually disappeared, cockroaches and their smaller relatives survived, continuing to evolve up to the present day. It was smallness, not grandeur, that became the key to enduring the harshest climate changes. This points to a larger lesson. In nature, no strategy is permanently optimal. Gigantism conferred advantages under certain conditions, but when the environment shifted, it was compact size, concealability, and rapid reproduction that allowed species to persist. That is why today our world still teems with ants, bees, cockroaches, and mosquitoes, while the Carboniferous giants exist only as fossils. Another factor shaping size limits was predation pressure. The Carboniferous can be seen as nature's experimental phase. At that time, birds and bats did not yet exist, and reptiles were only beginning to develop. This gave giant insects the chance to dominate the skies. But as more efficient predators appeared, birds with speed, bats with echolocation, any opportunity for giant insects vanished. An insect with a half-meter wingspan would struggle to evade the precise dive of a predatory bird. This pressure, combined with declining oxygen, brought the age of giant insects to its end. Today, even if oxygen levels were to rise again, other ecological factors, the presence of birds, bats, mammals, and humans, would prevent the return of giant insects. An oversized creature would more likely become easy prey rather than a ruler. In other words, that era was the product of a special combination, not easily recreated. But this does not mean we have lost wonder. On the contrary, by understanding that these creatures were not monsters, but real organisms existing in a unique context, we gain even more admiration for the diversity of life. The stories of Meganura, Arthropleura, or rochoids are not just about size, but about the boundless creativity of evolution. Some species reached their maximum and then disappeared, while smaller, humbler ones persisted, adapting and thriving in nearly every habitat on Earth. When sensational headlines depict dragonflies as large as hawks or cockroaches, the size of hunting dogs, the truth seems obscured. But science, with its care and evidence, reveals a picture even more captivating. A world where oxygen-rich air, misty forests, and the creativity of evolution allowed the seemingly impossible to become reality. And from that story, we learn a simple truth. Greatness does not always lead to success. Sometimes it is smallness and resilience that enable life to endure. In the world of the Carboniferous period, when the concentration of oxygen in the atmosphere was nearly 50% higher than today, the small creatures we are familiar with now became the giants dominating the forest layers. On the swampy ground, giant centipedes over 2 meters long crawled across the decaying leaves. In the dim sky, the broad wings of dragonfly ancestors beat leisurely, reflecting pale light through the dense atmosphere. It was a universe both familiar and alien. Giant ferns replaced pine forests, insects replaced birds. The key lay in oxygen. The larger a body, the greater its energy demands. With a respiratory system relying entirely on diffusion, today's insects are constrained by thinner air. But in a world flooded with oxygen, the airflow could penetrate deeper, nourishing larger muscles, allowing wings spanning half a meter to operate smoothly. Modern science has proven this by recreating oxygen-rich environments in laboratories. Insects grow faster, larger, passing the size thresholds impossible in today's atmosphere. Yet gigantism was not only a story of respiration, it was also a fragile trade-off between strength and biological limits. With each molt, an insect's body became soft, vulnerable to being crushed by its own weight. If a giant dragonfly appeared in today's world, it would become perfect prey for a small bird, simply because its recovery speed could not keep pace with modern predators. Researchers call this an evolutionary barrier. Once environmental conditions change, traits that once conferred advantages become burdens. But why are we so fascinated by these creatures? Perhaps because they evoke a world where insects, creatures we usually see as small, insignificant, became the ruling giants. Imagine a dense carboniferous forest when you look up and see the shadow of a meganeura gliding overhead, its wings buzzing like a natural helicopter. Each step on the ground carried the risk of encountering Arthropleura, a millipede-like creature as long as a car, its segmented body creaking as it crawled across the leaf litter. In that world, humans, if they had existed, would have been nothing more than small beings, entirely lacking in dominance. From a scientific perspective, the existence of those giants also reveals lessons about scaling laws. When a creature doubles in size, its volume and weight increase faster than its surface area. This means giant insects not only required more oxygen, but also had to contend with body weight issues. The exoskeleton, so effective at small scales, became less stable at larger ones. This is why vertebrates, with internal skeletons that could distribute forces more efficiently, had gradually replaced them as the dominant animals during the Permian and subsequent periods. Modern scientists still draw from these lessons for technology. Fossilized dragonfly wings, with their intricate veins, suggest methods of force distribution, inspiring engineers to design ultralight aircraft wings and small flying robots. The mathematical principles that once constrained giant insects are the very same limits engineers face when scaling designs up or down. In other words, natural history becomes a vast laboratory where millions of years of time have tested every scenario that human imagination is only beginning to touch. Yet human curiosity often comes with the thought, could we bring them back? In modern laboratories, the idea of genetic modification to resurrect a giant meganeura inspires fascination, but also stirs ethical debates. Such a creature, if born, would face a world not made for it. No oxygen-rich air, no suitable ecosystem, and no place in today's stable food chain. Even if humans could create an artificial environment, the larger question remains, should we do it? Because biology does not operate in a vacuum. Every species is part of a complex web of ecosystems. Just one misplaced introduction can devastate the balance, as with invasive species that have caused destruction across vast regions. A giant insect, if it truly existed, would not simply be a scientific experiment. It could become a threat to the very stability of today's environment. Looking back, the allure of the Carboniferous does not lie in resurrecting those creatures, but in allowing us to imagine a completely different world, where the laws of biology functioned under a different atmosphere, a different rhythm of life. The fossils left behind are not only evidence of the past, but also mirrors reflecting the limits of biology today. They remind us that life is not a single stream, but millions of possible paths, some of which have closed forever. In the shadows of the Carboniferous forest, the slow beating wings of Meganeura may once have been the soundtrack of late afternoons. And today, when we hear the soft buzzing of small dragonflies over a pond, it is still the distant echo of a majestic past. The giant insects are gone, but the lessons they left about biological limits, the power of the environment, and the fragile interconnectedness of ecosystems still resonate to this day. If we could set foot once more in the damp forests of the Carboniferous period, we might find ourselves wandering into a world both familiar and strange. These forests were unlike any tropical rainforests of today. They stretched vast and dense, with trees crowding together, rising tens of meters high with straight trunks like colossal pillars. There were no flowers, nor brightly colored sweet fruits as in modern forests. Instead, there were tree ferns, primitive giant conifers, and towering lycopsids, casting over the entire landscape a deep, almost shadowy green. An oxygen-rich atmosphere allowed creatures that breathed through tracheal tubes like insects and spiders to grow beyond their usual limits. Dragonflies the size of hawks glided gently through the forest clearings, while on the damp ground below, giant millipedes over a meter long crawled slowly across the decaying leaf litter. But nature did not stop at its majestic appearance. The fascination lies in how these ecosystems functioned like a gigantic biological machine, continuously absorbing and storing solar energy in the form of carbon. Plants of this era had structures rich in lignin, a compound extremely difficult to decompose at that time. As a result, when trees died, their trunks did not fully rot, but instead accumulated in vast swamps. Over millions of years, layers of plants buried under mud and oxygen-poor water gradually transformed into coal. That was the time capsule containing both biological and climatic history, which hundreds of millions of years later became the fuel that propelled humans into the industrial age. During that same period, biological atmospheric feedbacks unfolded slowly but powerfully. As more carbon was buried underground, oxygen levels in the atmosphere rose. Oxygen concentrations exceeding 30% allowed giant organisms to thrive, but also made Earth more flammable than ever before. Paleontologists have found traces of charcoal in sediment layers, proving that forest fires were once a force shaping the landscape. A single lightning strike could ignite a blaze that raged on, consuming the dense vegetation. Those rings of fire then returned carbon to the atmosphere, maintaining a fragile balance. This rhythm of burning, regeneration, burial was one of the fundamental engines that helped the planet regulate its climate for millions of years. Today, when scientists look back, they see not only giant fossils or glittering black coal seams, they see a sophisticated carbon cycle that Earth itself engineered. The ancient forests were both lungs and reservoirs, storing vast amounts of greenhouse gases and creating a world where oxygen was so abundant that insects could become winged giants. This also raises a profound question for the modern era. If nature once altered the atmosphere to that degree, could the rapid, large-scale actions of humans push the planetary system into an entirely different state? Such a comparison reveals the vulnerability of today's world. Millions of years of carbon storage in coal have been released in just a few centuries of industry. Sparks from factories and steam engines have returned to the sky the gases that an entire geological era labored to bury. When we look at the giant insects of the Carboniferous, we do not only see the wonders of evolution, but also a mirror. Oxygen once rose high, then declined. Forests once spread wide, then vanished. Climate once fluctuated, pushing life into new evolutionary paths. Are we today stepping into a similar phase, a climate shift created by our own hands? Yet science does not end with warnings. Research into giant insects, coal, and ancient atmospheres is opening new perspectives for modern technology. Aerospace engineers learn from the wing structures of dragonflies to design more agile drones. Climate scientists use coal seams and fossil plants to model how carbon and oxygen changed in the past, thereby predicting the future. Even researchers in biorobotics observe how small insects operate their bodies in different environments to inspire machines better adapted to change. What makes it all so compelling is the connection. A 1 meter long millipede may seem like nothing more than a strange creature of imagination, but in the broader picture, it becomes a living witness to the deep relationship between atmosphere and life. These creatures remind us that evolution never works in a vacuum. It is always a negotiation between biology and physics, between the limits of the environment and the capacity to adapt. And the lesson for humanity is this: to endure in the long term, we too must learn to negotiate with nature, rather than trying to overcome it at all costs. On a cultural level, the image of giant dragonflies or centipedes as long as snakes has a special power to awaken curiosity. They are gateways, leading the public from an initial sense of wonder to deeper stories about climate, ecology, and the carbon cycle. A teacher might begin a lesson by showing the picture of a dragonfly with a wingspan of nearly a meter, then expand the question: why were they so big? Why are there none like them today? Such questions draw listeners into a dialogue between past and present, between fossils and atmosphere. Science, in a sense, is always the art of storytelling. The shiny black coal fossils, the faint wing impressions on shale, all become words in an ancient book that we are still in the middle of reading. Each page turned not only recounts strange creatures long vanished, but also whispers the rules by which Earth operates. And as humanity faces today's climate change, that book becomes a map, pointing out that life has always been tightly bound to the atmosphere and that the choices we make today will leave deep traces in the future. It is no coincidence that nature chooses to whisper rather than to shout. In every layer of rock, every tree ring, every slab of coal compressed beneath the earth, there exists a kind of silent memory, a memory that does not belong to any individual but to the entire earth. The giant insects with wings heavier than the letters of an epoch are proof of that. They were not the product of whim, but the result of millions of years of negotiation between biology and environment. Each beat of their wings was an answer to atmospheric pressure, to oxygen levels, to the structure of the forests. And it is here that we encounter a timeless truth. Life does not develop in a vacuum, but in dialogue. Imagine the Carboniferous era as a colossal instrument. When oxygen rose to nearly one-third of the atmosphere, trees burst into towering forests, and insects spread their wings to new frequencies. It was a melody written not in notes, but in molecules. The atmosphere itself was the conductor, guiding the rhythm of size, form, and even the way life chose to fly, crawl, or hide. If giant insects were a crescendo, then the subsequent decline of oxygen was a necessary pause to open a different movement. Without that decline, we might never have witnessed the rise of birds or the grace of bats in flight. In those humid swamps, a gigantic body was not only an advantage, it was also a trial. An exoskeleton thick enough to protect was at the same time a limit on what could grow inside. A pair of wings large enough to lift also meant energy consumed many times over. Every evolutionary design was like a double-edged blade, and nature never granted without demanding a price in return. That is what made existence so fragile and yet so profoundly creative. Without the tension between advantage and constraint, there would be no innovation. As those giants gradually disappeared, they left behind a void. But nature never lets a void last for long. That space was swiftly filled by smaller, quicker creatures adapted to a world in flux. In the dim light of the ancient forests, the tiny dragonfly flicked its wings by the same rules its giant ancestors once obeyed. Smallness was not failure, but a form of refinement and optimization. If gigantism was a symbol of excess, then smallness was a symbol of efficiency. Thanks to that, life endured, expanded, and diversified. What is fascinating is that those same rules are still whispering within your body today. Your heartbeat cannot race forever without exhaustion, just as insect wings cannot grow endlessly without shattering. Your chest expands and contracts in rhythm with the oxygen cycle of the atmosphere, mirroring the same principle that once let the giant griffinfly soar over carboniferous skies. Your bones are thick enough to resist gravity, yet not so thick as to hinder agility. All of it is a delicate balance, and that balance is no different from the invisible contracts ancient insects once signed with the air. When we look at a fossil, we do not just see a lost creature. We see the entire web of connections that created it. A dragonfly's wing imprinted on stone carries within it the memory of ancient forests that burned into coal, of rivers that once nourished moss, of a sky so dense with oxygen it nearly ignited. That fossilized wing is a panoramic photograph, taken in the light of time. And when we place it beneath the lens of science, what emerges is not just form, but rhythm. That rhythm still echoes in lungs, in crimson blood, in every living being that exists today. There is a deep humility in realizing that no species is an eternal pinnacle. Gigantism was only a chapter, not the whole story. The giant insects of the Carboniferous did not vanish because of failure, but because they had completed their role in the biological symphony. Thanks to them, carbon was locked away in seams of coal, shaping the climate, providing a foundation for later life. And when oxygen ebbed, the smaller ones stepped onto the stage, not as reluctant heirs, but as new performers continuing the song. Looking at the present, we too are standing on a similar threshold. The atmosphere, the oceans, the forests, all are still negotiating with life. We, as a newly arrived species, are not exempt from this game. We grew powerful thanks to coal, the direct legacy of the Carboniferous, but we are also paying the price in a changing climate. And once again, the lesson of the ancient giants resounds. Every advantage comes with a cost. In the end, when you picture those colossal wings gliding over the swamp, remember that you are not just gazing into the past. You are looking into a mirror. That mirror reflects the endless relationship between life and environment, between ambition and limitation, between greatness and fragility. And perhaps in that reflection, what matters is not the size of the wings, but the shared rhythm by which we all continue to fly.